I do want to finish up this stuff. This is sort of your typical 131. We're doing everything in this class so far pretty in depth, I think. But these ones, these last chapter or sections 13.6 and 13.7, I think we'll treat with a little bit more of a light touch. There are some equations. You should know how to sort of, just implement those exact equations that are shown to you. You should have an idea of what the concepts are, but we're not going to go in depth in those last couple sections. But one of them is about shock absorbers. So you see this car with a shock absorber on it. If every time you hit a bump, it bounced in simple harmonic motion forever, then that would not be good. So what they do is they actually put some damping in here. They put a fluid, an oil in there to slow it down, and they try to critically damp it. We'll talk about that a little more later. I also want to say that I believe there's hope. Hope. And this is why. So you're at 56%, and there's 8 more days to evaluate this course. So if you do the math, 771 students, we only need 9.1% more. Only 70 students need to fill out the course evaluations, and boom, you'll all get that 1%. So if you know anybody who hasn't done it yet, you should tell them there's hope. I think it's going to happen. That's my prediction. Things are going well. But don't, if you haven't done it, I'm wagging my finger at you right now, which is the pendulum. So let's think about how a pendulum works. And in fact, I want to analyze this pendulum in terms of the net torque. So what is it? So the object is a mass on a string. And if you have good eyesight, you'll see I have a couple of balls hanging on strings over there. But the idea is that it's fixed up here at the top. This is the pivot, fixed point. This is like a string, which we're going to assume is like massless, I guess. All the strings in this course are massless somehow. And then there's the mass. It means that you neglect the mass of the string because it's much, much smaller than the mass of the bob at the bottom. So if you want to find the net torque, the Freebody diagram of M is going to be, what are the forces acting on it? Well, we've got gravity, mg acting down. Any other forces? Tension? Good. I think those are the only ones, tension acting up. So the torque of the tension is equal to 0 since the force line passes through the pivot. Does that make sense? This has got a 0 lever arm. So if R and F are in opposite directions or something like that. So this force line of, if that's tension, goes all the way through the pivot. So there's no torque from the tension. So the only torque is the gravitational torque. So net torque is T gravity, right? So what you have to do there is find that lever arm. So if this is the downward force, mg, then you can make one of those lines, force lines through it. It goes all the way up here. And I think that this up here is the lever arm. Okay, so torque of gravity is equal to L times mg, where if you look at your right angle triangle there, it looks like this. This is your theta. Here's your right angle. Here's a little lowercase l. Here's your L. So sine of theta is equal to the lever arm divided by L. So this is equal to mg capital L times sine theta. And then is it direction? If you are pulling downwards on this and the pivot is up there, is that a clockwise or counterclockwise torque? Well, it wants to pull it down, so it's going to go kind of this way. So that's clockwise. So it's negative. And so negative. So in other words, the torque net is negative mgl sine theta. Oops. Got it? And that'll go on my next slide. And the reason we say that it's negative is because we've defined positive theta to be going counterclockwise. Okay? We've actually defined theta equals 0 to be down, and theta to be increasing from that sort of negative y-axis or something. And that's important. So let's go to this busy slide. Here we are starting with that equation we just derived, and let's go through this stuff. Okay, so the net torque is going to be equal to the I, the rotational inertia, times alpha. Remember that one? So torque net is equal to I times alpha. That's Newton's second law for rotation. Instead of F equals ma, you've got the torque is equal to the rotational analog of mass times the rotational analog of acceleration. Okay, and that's d squared theta by dt squared. So that's just that. And now, what I've done is I've done the small angle approximation. Sine theta is approximately equal to theta. And now I've got this equation, mgl, instead of sine theta, I've just got theta. So that's a roughly equal to. Put a little, I'm going to just pretend it's equal. And now I have this, which is the second time derivative of something is equal to negative a constants, times that something. Ding, 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 that means we have simple harmonic motion. Anytime you have something that looks like double time derivative of x equals negative a constant times x, that's simple harmonic motion. Except instead of x here, we have theta. So the solution is that theta is equal to a cos omega t plus phi sub 0. We're now, the frequency of oscillations is omega. So omega is a constant here. This is not the angular velocity. It's a constant. And it's equal to the square root of whatever this constant was in that motion equation, which was mg L over I. And then the other thing you can do is, since you've got a mass on a string, you can use the equation mr squared for the rotational inertia. It's just the mass times the distance from the pivot squared. And this, actually, r in this case is L, so it's just ml squared. When you plug that in to up here, it's equal to the square root of mg capital L divided by ml squared. The m's cancel, so the mass doesn't matter, and this squared cancels with this L on the top, and you get square root of g divided by L. So that's the angular frequency of a simple pendulum. So we did this in the pre-class video. The pre-class quiz this morning, the first one was a frictionless pendulum clock on the surface of the Earth has a period of 1.0 seconds. On a distant planet, the length of the pendulum must be shortened slightly to have a period of 1.0 seconds. What is true about the acceleration due to gravity on that planet? So the period, remember, is equal to 2 pi divided by omega, because the omega, the whole definition was that it's 2 pi divided by period. And so that's going to be equal to 2 pi times the square root of L over G. And so if you've had to shorten the L to get the same period, you'll have to decrease the G a little bit as well. So L and G both decrease, I think, so that L over G is the same as the 1 second. That was my reasoning for that one. Let's do a Learning Catalytics question right now. See if you're getting this. Two pendula have the same length but different mass. And we actually even have a demonstration for this one. The force of gravity is larger for the larger mass, so which will have the longer period? I'll give you 1 minute to think about that. Click an answer, discuss, make sure you and your neighbor agree. And showing the results. Yeah, so the idea there is that it's the period, again, is 2 pi divided by omega. It's determined by the length of the pendulum and the acceleration due to gravity. G here just equals 9.8. So the mass is canceled out. And if we do that with this, we have sort of a light ball, I don't know, styrofoam ball, and we have a significantly heavier hockey ball, and we pull them both at the same small angle and release them. They sort of oscillate together, even though the force of gravity is much greater for the orange one. Let's do another. This one I just wrote up because I was kind of thinking on the way over here or back at my office. I thought I would do a little review quiz because this is kind of related. It looks really unrelated, it's a review, and you're only going to see it up on the screens. Can we maybe send it to all 3 screens, please? Let me read it to you. A marble and a bowling ball are released from rest at the top of a hill. It's one of these racing, like we did those soup can races, at the top of an incline, and they both roll without slipping. Which reaches the bottom first? And in both cases, I think the rotational inertia for a solid sphere is I equals 2/5 mr squared. But they have very different masses. So what's going on here, we did do a derivation of this way back when we did the rolling without slipping. It certainly matters what the ratio of the rotational inertia to the mass is. So the shape, the kind of object it is. So it's in fact this constant I equals c times mr squared. So this constant does matter, and it determines who the winner is. But the mass cancels out of these equations. And I find that, and it's the same for the pendulum, in a lot of these systems, when gravity is the driving force and the source of the energy behind what's moving, the mass turns out to cancel. It's always on the top and the bottom because it's the inertia, and it's also proportional to the net force. So when the net force is coming from gravity, usually the m's cancel, and they did when we did this whole thing. So if you got that one, that's good. Not a lot of people did. Okay, so there's 3 answers and a third of you got it, so maybe. A simple pendulum swings back and forth with a period of 2.2 seconds. What is the mass of the swinging bob at the end of the pendulum? Okay, so the period, once again, is t equals 2 pi times the square root of L over, yeah, okay, never mind. Can't do it. It doesn't depend on the mass, right? So that was a trick question, sorry. Thought I was about to do a math problem. Can we see this? I'm going to zoom out a little bit. So I'm all psyched about Luke and Leia coming up in this. Is that working? Just went a little bit further. But back when they were young, they did this famous scene where they grabbed onto each other and they swung across this gap in order to, I don't know, get out of the Death Star or something. I don't know where they're going, but they needed to cross a 10-meter horizontal gap. and there was a beam, so you can try to draw this. Just got my notes here. So this is the way I drew it, is that here's the beam, and here's the gap, so they're standing here. And they want to swing across it. So this is your 30 meters, and this is your 10 meters from here to here. And it actually asks, if they start from rest and swing down and up, just reaching the other side, how long does this take? So you can draw a Freebody diagram at the start, which will look like this. You'll have tension acting up, just as they let go, I guess. So after jumping, I guess. So there's no normal force. So then you've got gravity acting down, and I think that's it. And they're going to accelerate in this direction. And so we can tilt our axes, I guess, if we want. Set x to be this direction, y to be this direction. And we can say that F net in the y direction is equal to 0 because it's not going to accelerate up or down the string. And so F net in the x direction is equal to mg times sine theta, I think. See, this is the problem, is that it's not constant. Theta is going to go down to 0 and back up the other side. So this is not a constant force. We're kind of not able to solve this. Okay, well, I could write a Python program to solve it. We can't, but there's no easy solution. It's not constant acceleration. So what we're going to do instead is not constant acceleration. That's our problem. So we can't do that. We could write a computer program, but what we could do is we can use a crude approximation, which is that we can assume that sine theta is theta. Simple pendulum. Sine theta is approximately equal to theta. So that's what we're going to do. I'll get some more paper. Once you do that, then it becomes a simple harmonic motion problem. So what you've got is simple harmonic motion. They're going to oscillate back and forth. They're just going to swing back and forth with oscillation frequency is omega is equal to 2 pi over t is equal to the square root of g over L. And then, so, you know, again, the period is going to be 2 pi times the square root of L divided by g. And then what you can do is say, well, one period, t is the time to go twice across the gap. But Luke and Leah don't want to get back where they started, because then they're still going to get shot at by stormtroopers. So they're going to get off after half a period. So they'll be on the other side of the gap. Make sense? If you go the whole period, you might as well not have jumped at all, right? So, okay. So t over 2 is the time to cross once. And then you just plug in. So t over 2 is equal to just pi times square root of L over g. So it's 3.14 times the square root of 30 divided by 9.8. So I got that it's 5.5 seconds. Oops. How's that? Okay. So what we did here is we used this, the crude approximation is that sine theta approximate equals theta, so maybe they're roughly a simple harmonic oscillator. So I'm going to put on what our conditions are for simple harmonic motion on this single table. Say we started here on the left with mass on a spring. We said that if the spring obeys Hooke's law, F equals negative kx, then you've got an angular frequency of square root of k over m, where m is the mass of the object that's attached to the spring. Now, it is possible to overstretch any spring. Certainly, the spring itself is made of coils, so if you stretch it out to the length of whatever that coil is, it's no longer going to be a spring, and it's not going to obey Hooke's law if you destroy your spring, right, or overstretch your slinky. So that's kind of the real, there really is a small oscillations condition for even mass on a spring, which is that it really shouldn't go too much to violate Hooke's law in the spring. And then for pendulum, it's small angles. We used an actual small angle approximation, sine theta equals theta. So this is not really the solution for pendulum. I mean, if you go way up to 90 degrees, then it's not going to obey this frequency. But for small oscillations, just a little push, and you get square root of g over L. Let's do another learning catalytics. Well, this is actually the third one. And you only get the picture on the front screen. You don't get it on your device. But a person is swinging on a swing. When the person sits, not sits still, but just sits, then the swing is oscillating back and forth at some frequency, f or something. If instead of sitting on the swing, the person's standing on the swing like this girl, then how does that change the frequency of the swing? Is the frequency while you're standing greater, the same, or smaller? Give you a minute to think about that. So there you go. I think it's actually a greater frequency, and my reasoning is that I think that distance L is the distance between the pivot point and the center of mass of the object. So I don't think that the chain stretches when she stands up. It's a metal chain after all, and she's a little kid, right? So I think what happens is that her center of mass gets closer to the pivot point, thereby reducing capital L. So remember, the frequency, natural frequency, is omega equals the square root of g over L. Okay, so standing, I think, reduces effective distance, or the distance actually, between, I guess, the center of mass and the pivot. It's kind of a tricky question, isn't it? So L has then decreased, and it's on the denominator, so omega has to increase. You could try it, measure it, I guess. I'll do another one. Okay, another weird one. This is the fourth one. Maybe this one, I hope, is not quite as difficult as a lot of the other ones. This is more a plug into an equation one. A grandfather clock at high altitudes runs A fast, B slow, or C the same as it does at sea level. Doesn't matter. You want to think about that? So I actually think you make a good point. The answer is kind of C, right? It's not going to change much, but it's not C. So I put B. So I think that the force of gravity is about the same as it is on the top of the mountain as it is down on the ground, right? So it's not going to change that much because you haven't moved much relative to the radius of the Earth. But what I was thinking is that if you look at the grandfather clock every day and set your watch to it or something, and you look at it for 2 months later, unless it's super, super precise, it's either going to lose time or gain time. And that's what this question is about, is that I think if you go up, gravity will decrease slightly, right? Okay, lower instead of 9.8, it's like 9.79 or something like that. You get me? And then and then it's just the period, which is what you want. Let's see what the period is. It's 2 pi times the square root of L over G, right? Longer period for a longer L. So if G decreases, then the period increases. So it's going to tick slower. Instead of 1 second between, it'll be 1.001 seconds or something. And so it's called a slow clock. Make sense? Times it. Pretty good here. Okay, so I want to just tell you something interesting about uniform circular motion versus simple harmonic motion. Seemingly unrelated, but uniform circular motion was when you're going around in a circle, okay? And I'll actually draw it like this. Here's the x-axis, here's the y-axis, and you have some omega is equal to the angular velocity is a constant. And here's your object, and Vt is equal to omega times r, where this is your r here. And if you think more about that, we could look at what is x? Well, you have, here's your r, here's your little theta, here's your right angle, here's your x. So I think that actually the cosine of theta is equal to x divided by r, so x is equal to cosine of theta. And also we have that theta final equals theta initial plus omega times time. And if theta initial equals 0, because you start at the x-axis, then theta is equal to omega times time. So I guess x equals cosine, oops, there's an r missing, r times cosine of omega times t. See the r there? Anyway, and this r is a constant. And then simple harmonic motion, which is that you've got a mass on a spring going this way, then where you start with is you say that acceleration in the x direction is equal to, negative omega squared times x, and then the solution, we said this trial solution is that x is equal to a times cosine of omega t, where a is a constant. So I'm just pointing out here that mathematically, simple harmonic motion is identical to one component of uniform circular motion. Something that you may have noticed if you just look at these equations. And then, I think this is from Wolfson, is just showing that. So, example, if you have something on a turntable going round and round, and there was like a light shining the shadow of it over to the side here, and you had maybe a mass on a spring going up and down, the mass and the spring would trace out exactly the same motion as the shadow of the thing on uniform circular motion. Sort of cool coincidence. Okay. And that's why you use the same omega in radians per second for both things, even though they're very different. Is that math-wise they're the same. Okay, I'm going to go on to this energy, because this is the last sort of in-depth important thing of this chapter, and then we'll talk a little bit about the damped and driven. So energy of mass on a spring. We're going back to our horizontal spring, because that's a little easier than the vertical one. Here's a mass m. Here's its whatever, x equals 0. is spring equilibrium. That's important. Because then what we have, so actually the solution, so position. The position of the mass in the spring is x equals a times cosine of omega t. And also the velocity, we figured that out before, v sub x is equal to negative a omega times sine of omega t. Okay, so energy. We're going to say the total energy is equal to the kinetic energy of the mass, 1/2 mv sub x squared, plus, is there any other form of energy in this? 1/2 kx squared. The spring itself stores energy. And it stores energy such that if the spring is at equilibrium, there's no potential energy in the spring. It can't do anything. But if it's stretched or compressed, you get 1/2 k times x squared. So this is positive even if x is negative. This is an x squared. Actually, both these are positive. It's always positive kinetic energy, or 0. And it's always positive potential energy of a spring, or 0. So that's kind of interesting. But anyway, so it's got some energy. We can plug in these equations now to figure out what the energy is in terms of time. So plug that x into there, and plug that Vx into there. It's going to look a little ugly, but we got lots of paper. Let's do it. E equals 1/2 m times negative a omega sine omega t squared, plus 1/2 k times a cosine of omega t all squared. And now I'm going to go up, so curve that a little bit, and try to simplify this a little bit. We can use the fact that omega is equal to, omega squared is equal to k over m. And we can say then that E is equal to, we're going to pull out the A. So we're going to pull out a 1/2 factor, and I'm going to pull out an A because there's A in both of them. And we're going to say that it's mass times omega squared times sine squared of omega t, and then plus k times cosine squared of omega t. So I'm going to plug this into here. I'm going to say that this is now equal to 1/2 a. This is supposed to be a squared, sorry. The a is squared in both of these terms, so there's an a squared, and then there's a, now I can pull out a k and say that this is now sine squared omega t plus cos squared of omega t. Does anyone know what sine squared plus cos squared equals? Boy, you guys are from high school. Okay, good. That's very good. So that's it. So we write it as the total energy of a simple harmonic oscillator is 1/2 k times a squared. And then this is sort of an exercise for the student. This also is E total equals 1/2 k times V max squared. Where V max, remember, is just the A omega. It's the maximum speed. Those turn out to be the same. And it kind of makes sense if you think of maybe a graph of it. Let me put up this slide next, which is that when the thing is, let's see here, kinetic energy is the green line, and potential energy is the blue line. So at the beginning, the kinetic energy was 0. This is when it's released from rest at its maximum amplitude. No kinetic energy, but it's sitting up there at x equals a. So right at here, I think, is x equals a, and so the spring is stretched a, so its potential energy would be 1/2 k a squared. And then, once the spring goes back down to 0 stretch, that's when the thing is moving as fast as it's going to go. It's V max. So I think this will be, right at this moment, will be when V is equal to V max. So that's why, and they're both equal to the total energy. When the one drops to 0, the other one becomes that total energy. But all the time in between, if you add these two up, they just slosh back and forth, and they add up to the same total energy. And there was a quiz from this morning which said that if you double the amplitude of a vibrating ideal mass and spring system, the mechanical energy of the system, which is E equals 1/2 k times a squared, will go up by a factor of 4. You just plug a 2 in there. So A1 equals 2a, so E1 equals 4a, E. Something like that. I think we're on to the last little bit here. I've only got 8 minutes, but I'll just introduce a little bit of those light touch sections at the end, which is that the problem with all this simple harmonic motion is that cosine is forever. Cosine was always oscillating, and it always will be oscillating, but we know in real life, whenever you set something oscillating, unless you add some energy to it, it just slows down and stops. So, we have to, in order to model that, what Wolfson does is he says, okay, mass in a spring, but now we're going to add a new force, D, which is called the damping force. It's like friction. It's a dissipative frictional force. And it's proportional to its speed, actually, and it's kind of like air resistance, for example, as an example. If you are moving through the air is a fluid. The fluid has to push out of the way as you plow through that fluid. The faster you're going, the more you have to push away, and so the more the resistive force is to your moving. When you add that, then this is going to get a little ugly, so bear with me, but Wolfson says that if the drag force has a magnitude D equals B times V, so it's equal to some constant B times the speed V, then the solution is x equals some constant times e to the power negative bt over 2m, so that's in some sort of exponential, times cosine omega t plus phi. So this is your old simple harmonic motion, this part. But then you multiply it times what's called a decaying amplitude. Sometimes I call this the envelope function. You've got some envelope, which is the dashed line, which is shrinking the function itself, which is the cosine. Envelope of the amplitude decays exponentially. So it's one of those equations which you might write on your aid sheet. Certainly you don't have to derive this one or even show that it's true. But if you plug that into, the whole differential equation where you've got two forces now, you should get it. Let me go through a little bit here of some questions from this morning. Is B just a constant that is dependent on the system? Yes. So B it's the drag constant, I guess. It depends on the thickness of the fluid that you're going through. If it was air, it would be less than if it was water, for example. It depends on the shape of the object. Obviously a parachute or something, if it opens up, then your B is going to weigh increase. What are the units of B for the damping force? If F equals B times V, then is B kilograms per second? Then you got it, that's exactly right. Somebody answered their question right as they typed it. Just to clarify, the object's mass does not have an effect on the period of a simple pendulum. We talked about that already. Usually when gravity is the driving force, the mass is not important for the motion. How do we remember all these equations? Write them on your aid sheet. That's what I would do. I think that, honestly, you've got two sides of an aid sheet. You could probably write every important, unmemorizable formula from chapters 1 through 14 on that one sheet without a very fine-tipped pen. Are rigorous proofs ever used in physics? Well, I guess it sort of depends what you mean by physics. If what you think physics is physics 131, then I guess not. But physics to me is a research field, right? In order to do theoretical physics research, then you need to use math. And math, of course, is nothing but rigorous proofs. That's what we do. Please add the practice feature in Mastering Physics assignments. I thought that I already did, and I've been looking at all the settings for all my Mastering Physics homeworks, and it seems to say practice is allowed, rework for practice is checked. So I can't understand what's happening there, so if someone wants to come with their laptop during office hours, I'll have my laptop and we can try to fix this problem. If you're not being able to practice your homework, that's not good. Simple harmonic motion is how I thought I was going to do my homework. Damped oscillations model how I actually do. Okay, that's just funny. I thought it was funny. All right, and then lastly, you've got a little bit of time. I want to talk about driven oscillations and resonance. If you've got an oscillating system that, when left to itself, oscillates at some frequency f sub 0, we call that the natural frequency. Example would be f sub 0 is equal to, I think it's 1 over 2 pi square root of k over m for mass in the spring. That's your natural frequency. Then what you do, it seems a bit random, but you suppose that the system is subject to a periodic external force that has a driving frequency. This is called the driving frequency. Driven system oscillates at f external. The amplitude of the oscillations is generally not very high if f external differs much from f0. But as it gets closer and closer, even if it's a small driving force, the amplitude goes way up. And there is this idea of resonance, which is if it's the driving frequency, it can be at different frequencies, and this is the natural frequency, then it goes up. So if you are sitting on a swing, well, there's some natural swinging frequency for the swing. And you can give yourself a little push by moving your legs, right? And if you do it really fast, you know, nothing much happens. Or if you were to do it really slow frequency, nothing much happens. But if you move your legs to be the same exact frequency as you normally swing with the swing, you get higher and higher and higher and higher. Little kids discover this. Even if you're 5 years old, you kind of figure this out. And eventually you can pump yourself up with, even though your mom is over on the bench talking to another mom, you can get way, way, way high up with only a small little input force of just your legs going back and forth. So, and want to do this demo? So here I have, Kevin has set up these different saw blades, and these saw blades have their own natural resonance frequency that they want to oscillate at because they're sort of springy. And then we have a driving force over here which I can turn at different frequencies. So I can start it pretty low, and it's inputting a driving frequency which is oscillating at some frequency. And when it matches the big saw blade, then the big saw blade goes way high amplitude. If I crank up the frequency a little more, it should go to the next saw blade. Oh, that's still the first saw blade. There we go. That's the second saw blade now. I've got a resonance there. As I increase the frequency more, I should go to the third. Oh, a little more. Fourth one. Every time I match the oscillation frequency of one of the saw blades, then it becomes the one with the high amplitude. See how fast I can get it going. So I'm adjusting the resonance by adjusting that driving frequency. So that is it. Have a good weekend. I will see you on Monday. There's my little pre-class video, something to think about. 2 of the 5 senses depend on waves in order to work. Which 2? And I'll see you Monday.